Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a mini-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series number 2, A History of the Atom. Episode 7, The Periodic Atom. The next 3 episodes of the podcast are going to cover the same chronological time frame, roughly, but look at developments in atomic theory from 3 very different perspectives. The first will continue the thread of chemistry. The second will look at the development of electrochemistry, a boundary discipline between the longer established investigations of physics and the emerging science of chemistry. And finally, the third will look at the development of physical ideas of the atom from the areas of thermodynamics and statistical mechanics, which were predominantly in the realm of physics at the time. Before we go very far in this, a word is in order about physics, chemistry, and the relationship between the two. During the 18th century, physics was concerned almost exclusively with the motions of objects. 2 broad philosophical approaches have developed as programs of investigation, the mechanical and the dynamical. The first posited that the best way of approaching an understanding of why things moved the way they did was to think of them as physical objects subject to forces. This meant treating entities as things made of matter that interacted. This was the approach favored by Newton himself, as well as those who followed him, including, as discussed in the supplement, Dalton, who saw atoms as solid, massy, and hard. The other approach was known as the dynamical approach, and it tended to be more metaphysical. Rather than trying to postulate real entities and forces, it relied on mathematical descriptions of phenomena as the way forward to understanding what was going on. This was the tradition that the atoms of Boscovich appealed to. Neither approach really relied on matter being atomic to make progress, and as such, atomic investigations remained at the periphery of physics all through the 18th century and, indeed, well into the 19th. In physics, the problems of interest were the description of motion and force. Nevertheless, due to the interest in the behavior of gases and the nature of heat, there was some interest in understanding what matter was, and, with Dalton's proposal of the atomic theory, this began to move to the fore over time. As we'll see, when a more comprehensive picture of energy emerges in physics in the 1840s and 50s, the focus will begin to shift to a more fundamental exploration of the ideas of how matter was constituted. From 1810 through the 19th and into the 20th century, the nature of matter will be more of a chemical problem in many ways. As the atomic theory proves more and more useful in describing chemical reactions, there is a greater drive to explain why they happen, and that leads us into today's topic. On a final note, as we go through these 3 episodes, don't be too surprised to hear the same names over and over again. Figures like Berzelius and Davy did work in a surprisingly broad number of areas. Their research was in chemistry, and while the field had more or less passed from the domain of those sort of professional practitioners who had trained in some other discipline that was related, such as medicine or pharmacy, to academics more in the mold of Dalton, the field was not so specialized that a well-trained investigator couldn't do work in a broad range of areas within chemistry itself. Our story is going to follow 2 threads at this point. The first had to do with the identification of elements. With Lavoisier's destruction of the old Aristotelian elements and Dalton's establishment of a new atomic definition of what an element was, there was unleashed a torrent of activity to isolate and identify new elements. Some discoveries were made through chemical means, as was often the case with Berzelius and his students, while many others occurred due to the introduction of the use of controllable electricity using Volta's battery. We'll save the specifics of the development of electromagnetism for another series, but investigators like Davy and Faraday became masters of the technique of using electricity to separate elements, most notably sodium, potassium, and chlorine. As I've mentioned, one of the great challenges was to find the atomic weights of each of these elements, a work carried out in great part by Berzelius initially and also by Humphrey Davy and Alexander Dumas later. In this way, much data was gathered about the inherent physical properties of each element. However, there was an entirely different type of information that could be gathered, and that was about the chemical properties of each of the elements. What other elements did each element react with, and in what proportions? What was the nature of that reaction? Did it produce heat or absorb it? What types of acids, if any, might the element create or instead neutralize? While some of this information was known, especially about some of the metals, there were a number of compounds and reactions that remained pretty mysterious to chemists. The substances involved usually involved non-metallic elements, specifically carbon, hydrogen, nitrogen, and oxygen. As chemists began to work to study this specialized set of compounds, initially found almost exclusively in living things, the subdiscipline of organic chemistry began to develop. Michel Eugene Chevreul, whose life I appropriated in one of the recent podcasts, was a pioneer in this area. This is also one of the areas and one of the places where I must briefly summarize the work in order not to stall the plane of our narrative, to use my metaphor from earlier. There is much fascinating work done here at this time, but it can be somewhat technical for those without a background in chemistry, and it will take too long for us to develop the necessary concepts to be able to delve deeply into it. The interested student, of course, can find good discussions of this work in either of the sources I've previously referenced in regards to the development of chemistry, and I would encourage anyone who wants to do a little more study to look there. To sum up the relevant ideas that contribute to our discussion, what the organic chemists found was that a group of atoms could combine into certain very stable combinations that then acted as a unit, which was called a radical. And that unit, the way that it formed, had to do with an idea known as valence. Put simply, valence is a number that says how many connections an atom can make with other atoms. If we think of human beings, we have a valence of 2 because we can grab 2 things with our hands. Some of our primate cousins, however, have a valence of 4 because they can grab things with both their hands and their feet. In time, this concept of valence was generalized from just non-metallic atoms and things that showed up in organic chemistry to all atoms. Why atoms had different valences and even what caused valence in the first place was unknown, but the idea was extremely useful in understanding what type of reactions would take place given a certain set of elements. These 2 sets of data lead us into the heart of today's episode, and that has to do with the organizing of all of this information. As soon as data about a fair number of elements begins to accumulate, people began to look for patterns. It's something we human beings do really, really well. You know, there's this evolutionary advantage to seeing patterns in relationships and things. Our ancient ancestors began to predict and forecast, and that gave them a huge head start on survival. So, much like the hunter-gatherers they distantly descended from, some chemists began looking for patterns in the new atomic data to see if they could get ahead in synthesizing some new compound or finding some new element. That's the history we're going to focus on for the rest of the episode, and it will eventually lead us to a Siberian radical turned chemical prophet. First, though, we have to rewind a bit. Once Dalton's atomic theory started to disseminate, it was realized that there were a lot of elements out there. While there was no specific physical reason for any given number of elements, the intellectual bias was that there shouldn't be quite so many. Aristotle had only needed 4, and that just seemed a whole lot cleaner to everyone. As atomic weights began to be published, what was noticed was that a lot of the measurements were somewhat close to integer numbers. For low atomic weights, these values were well within the experimental error to a simple integer whole number. To illustrate this, let's think a little bit about carbon. The atomic or apparent weight of carbon might be measured by one chemist to be 12.2, while another chemist might arrive at a value of 12.1. While these numbers aren't the same, let's say that the error in the measurement for both chemists was about 0.3. What that means is that the first measurement might actually be anywhere between 11.9 and 12.5, and the second could actually be between 11.8 and 12.4. As can be seen, within the error limits, both measurements might actually be the same, and they could actually both be just 12. While there were certainly elements that didn't seem to follow this integer pattern, it was conceivable that the errors in measuring their atomic weights were large enough that they might also be shown to be integer values as measurement techniques improved. The first chemist to really buy into the idea of integer values for atomic weights was a British doctor and chemist by the name of William Prout. Prout did a lot of work in chemistry, especially in the study of living things, but it is his protyle hypothesis for which he is best remembered. First published in 1815, this idea was that all atoms with atomic weights greater than hydrogen, which has an atomic weight of 1 in this system, were just combinations of hydrogen atoms. In our earlier example, carbon wasn't its own type of singular atom as Dalton thought it was, but was in fact a combination of 12 hydrogen atoms. Prout called this particle a protyle and thought that it was a basic building block of matter. This idea quickly gained a lot of traction in Britain and had some adherents across the Channel in Europe, and there would be those chemists who would hold the idea pretty strongly up through the 1860s. So why didn't the idea stick? Why don't we now talk about protiles? Well, it's a case of a beautiful hypothesis being slain by ugly data. As the measurements of atomic weight got better, the value of several elements didn't actually move towards integer values, but away towards fractional values. The case study for this was chlorine, which no matter how many times people tried to measure its atomic weight, and no matter how accurately they did it, it seemed to stay right around 35.5. Since you couldn't have half of a fundamental building block, though there were some chemists that suggested this, Prout's idea lost a lot of its credibility. However, as some of you have already no doubt thought to yourselves, this idea will never quite go away and will find new life in the work of Ernest Rutherford in the early 1900s. Unfortunately, Prout was a man before his time. There was still too little understood about the atom, and so nobody recognized the idea of isotopes or had a realistic picture of the atom's internal structure. We'll get back to those things down the road, but at this point, Prout and his protyle must pass from the stage, at least for a time. Before we move any further forward, it might be useful for those of you not listening to this while driving or performing some other activity that requires your visual attention, to find a picture of a modern periodic table. We, of course, now know how everything organized out, but what I'd like to do is walk you through the historical development of that organizing. As we go through this process, you might find it helpful to be able to refer to a picture of this every now and again. I'll post one of these to the podcast website, www.thescientificodyssey.typepad.com, and also to our Facebook page. along with a few other diagrams that will help you see what we're talking about. For those listening while doing something that precludes looking at pictures and whatnot, I hope you can still remember the chart that was likely hanging on the wall of some chemistry or biology classroom you might have spent some time in. The important thing to remember is that the rows of the table are called periods and the columns are called groups. Okay, so 2 years after Prout published his protyle hypothesis, a German chemist, and I hope I pronounced this right, a guy by the name of Dobereiner, announced an interesting relationship that he had discovered. He found that certain groups of 3 elements showed similarities in the chemical behavior and had certain numerical properties. Calling these groups triads, he showed that the middle element had an atomic weight that was close to the mean of the atomic weights of the other 2 elements, one being higher in weight, one being lower in weight. Over the next couple of decades, in parallel with consideration of Prout's hypothesis, Dobereiner and others continued to develop this idea and find additional examples of these triads. The key idea here is that the triads revealed meaningful chemical relationships along with physical/numerical ones. A group of elements would be excluded if they lacked both, as was the case with nitrogen, carbon, and oxygen, which met the numerical criterion but not the chemical one. In modern terms, what Dobereiner and others had begun to see were what chemists call the groups or columns of the periodic table. What was much harder to suss out, though, were the rows or periods, because it was a lot easier to recognize the similarities of chemical behavior, especially once the idea of valence was established, than it was to see the underlying structure which would lead to the establishment of periods or rows on the table. Nevertheless, this work in triads was the first good attempt to organize the data about elements and find patterns. Unfortunately, as more elements began to get discovered, it began to become clear that the picture would be a little more complicated than they first expected. The idea of triads really rests on the fact that many of the elements discovered live in the top 3 periods of the modern periodic table, and that they are found in the left 2 columns or the right 5 if we exclude the noble gases in the modern table. Those elements we now know to live in the groups of the transition metals were harder to deal with as they were found in periods farther down the table. Hence, at best, the chemists trying to work with the triad model could only account for about half of the known elements. Now, that's not a bad start, but certainly not anywhere nearly inclusive enough to be seen as something more than just a curiosity, at least initially. As more elements are discovered, groups of 4 began to be recognized as sort of double triads, which begin to call into question whether the triad was the basic organizing principle at all. So let's move forward. In 1843, chemist L. Gmelin pulled together all of the triads in 4 groupings and put them into a V-shaped system of organization in the first volume of his handbook on chemistry, sort of a textbook that was being developed that discussed different types of elements. The system was unique in that it ordered the elements essentially and initially based on increasing atomic weight and then on chemical similarity. What's amazing about this system is that with just a little bit of artistic rearranging, it reproduces the main group of the periodic table surprisingly well. Now, it doesn't handle what we call the transition metals well, and it doesn't clearly display the periodicity that's so necessary for the periodic table's power as an organizing principle, but it does take a big step in that direction. The fact that Gmelin uses this structure as a way of organizing his fairly popular chemistry textbook will have significant impact on the next generation of chemists who used the textbook and grew up thinking in terms of his structure. In 1850, Max Joseph Pettenkofer noticed that within many of the groupings of the triads, and even larger groups, there were apparent weight differences of either 8 or 16 between the elements. For example, the apparent weight of potassium is 16 units greater than sodium, which is 16 units larger than lithium. At about the same time, Ernst Linsen was working to pull together all the known triads, and in doing so he discovered a relationship between them that allowed some of them to be grouped into what he called eneids or supertriads. He published his work in 1857 and made a number of predictions regarding the atomic weights of what looked to be missing elements. While these predictions turned out to be incorrect, the system, like that of Pettenkofer, pointed the way to a larger structure in the relationships between elements and emphasized the need not only to group elements based on their chemical properties, but to organize them somehow in terms of increasing atomic weight. The work I've just described, which represents just a fraction of the chemical progress made between Dalton's atomic theory and the rise of periodic systems, that period between about 1810 and 1860, forms the foundation of the radical organization of chemical knowledge beginning in the 1860s. I've touched on some of the areas of that development in the earlier podcasts, but the Karlsruhe Conference in 1860 seems to be the watershed moment that burst the dam, in a sense. It is at this conference, if you recall, that Stanislaw Cannizzaro presents an improved form of Avogadro's solution to the final and most vexing problems of Dalton's atomic theory. This allows chemists to finally arrive at very accurate atomic weights for all of the known elements. Actually, that's something that Cannizzaro had actually done previously and brought a lot of his data to the Karlsruhe Conference. While not well received at the conference itself, Cannizzaro's paper and pamphlet, whatever it's called, would be read by a number of attendees on their way home from the conference. In reading this, a number of these people would be converted to this explanation shortly after the conference by its power and its obvious applicability. With these final issues resolved, and with good atomic weights now established for almost all of the elements, most notably the gaseous elements, oxygen and nitrogen, the pieces of the puzzle were all finally on the table to work with. By adding these to the systems of Pettenkofer and Linsen, you have everything for a foundation that allows you to put the pieces together. Interestingly, over the next decade, there will be no fewer than 6 individuals who will do just that with varying degrees of success. These will range from the practical geologist Chancotois to the detail-oriented radical chemistry teacher Mendeleev. The key idea to all of these systems is that the organization of the elements is periodic. That is to say, that the chemical and physical properties of the elements themselves repeat in a regular way. The first person who seems to hit upon this idea was a French geologist by the name of Alexandre Émile Beguier de Chancotois. His system is rather amazing, as it is a 3-dimensional type of a thing with the atomic weights of the elements represented along a spiraling pattern, much like the threads on a bolt. The cylinder of the bolt was divided into 16 parts, and the thread, as it were, of the bolt ran at a 45-degree angle. So sort of think of the thread of the bolt spiraling upward. This allowed the 17th point on the table, or the 17th element in the table, to be directly above the first element on the cylinder of the boat. Thus, sodium would appear directly above lithium. This created vertically oriented columns which would correspond to groups in the modern table. This system was called the telluric screw and is really quite remarkable in representing the organization of the non-transition metals well a full 17 years before Mendeleev would do so. Unfortunately, the system didn't really make much of an impact on other chemists. The most important reason for this was that it was a complex system and it was difficult to represent in publication. In fact, the first printing of the article lacked the diagram necessary to understand the system at all. However, even with the republication of the article a year later, with the diagrams included, those diagrams were still almost too difficult to comprehend in flat two-dimensional form. I really have to wonder how well de Chancourtois' ideas would have been received if he'd actually been able to fabricate like a cylinder with the elements printed on the cylinder itself, stacked in the appropriate way, and then had it distributed to everybody. It just really is a fascinating thing to think about. Historically, the most well-known counterclaimant, as you might call him, to the discovery of a periodic system was a man by the name of John Newlands. A year after Descartes, Newlands presented his own periodic system beginning somewhere around 1862 and then developed over the years up through 1865 and 1866. He suggested what he called a law of octaves for the periodic pattern of element arrangement. While demonstrably correct, Newlands made the unfortunate error of comparing this to a musical scale in a presentation to the London Chemical Society in 1866. While it is unclear as to whether Newlands intended the reference to be just a simple analogy or something pointing to a more mystically connecting universe, the attendees of the conference took his comments in the latter vein, and because of that, ridiculed both him and his ideas. It should be noted, however, that this is not the only reason, and maybe not even the main reason, the idea was dismissed. The more important or more foundational reason probably had more to do with the British tendency to view most, if not all, theoretical work in the sciences with a lot of skepticism. This is a legacy in the concreteness of the modeling approach founded with Boyle and Newton, and most explicitly expressed in Dalton's atomism. It was also unfortunate, though, that Newlands was working at a time before the discovery of the Nobel gases. Or I should say noble gases, Had they been discovered, the rule would have been some sort of a law of nonets or nines, and the whole analogy with the music scale would never have happened. At the same time, Newland's countryman, William Oddling, was working on similar research, though due to his more established position in the English chemical community, Oddling had access to better and more precise measurements of atomic weights. Oddling's contribution to the growing attempt to organize the elements was to recognize that there are several metallic elements that seem to be separated off from many of the other elements. These metals would become what are now known as the transition metals, and their removal from consideration from the main group of elements made many of the periodic patterns much easier to recognize. Lothar Meyer would incorporate this work into his periodic table almost verbatim. As a side note, there's sort of a story that Oddling had a lot to do with blocking the acceptance of Newland's ideas in the British scientific community. Research has pretty much shown, at least by the historians, that that's probably a misnomer. Doesn't look like Oddling really stood in the way of anything that Newlands did, and certainly didn't mean that, or it didn't keep him from being published. It just had to do with, I think, as much as anything, Newland's unorthodox approach to presenting his ideas, and, the fact that it was just so theoretical. Now, perhaps the oddest contributor here in this first initial group of four was the polymath Gustavus Heinrichs. Heinrichs was a German who had immigrated to America and had settled at Iowa State University, first as a professor of modern languages and later in natural philosophy. Heinrichs was about as eccentric a person as you can imagine, and I can't even begin to go into here all of the details of that. Among his many contributions, he is credited with having established the first permanent meteorological station in the United States in about 1875. It should also be noted that there's real divergence of opinion on Heinrichs among historians and scientists alike. While there are some that view him as one of the 6 legitimate developers of a periodic system of the elements, others see him as a scientific maverick and kind of a crank. The truth probably lies somewhere in the middle of both of those positions, and it can be shown, at least in terms of his chemical researches, that Heinrichs was really onto something in how he was taking a look at things, even though you had to pick through a lot of eccentricity to get through that. So, Heinrichs' unique contribution was to recognize the role of spectra in determining atomic dimensions. We'll deal with spectra in a later series of podcasts on light, so let me just say a couple of things so we can move forward. First, a spectrum is what you get when you shine light through a prism. If that light is from a heated source, light from the filament of an incandescent light bulb, for example, the spectrum looks like a rainbow. You get all the colors, red, orange, yellow, etc. However, if the light is produced by burning a single element, or compound, or by running a spark through a pure gas, the spectrum will look like a series of discrete, bright lines with black spaces in between them. Second thing to note is that Gustav Kirchhoff and Robert Bunsen, who pioneered this method of what we call developing bright line spectra, had shown that each element or compound gave off a unique one of these. Now, while these had been of much greater use in the field of astronomy initially, Heinrichs was able to develop a relationship between the spacing of the bright lines in an element spectrum. He saw that for any particular element, the frequencies of its spectral lines were whole number differences of the smallest difference. In calcium, for example, the ratios might be 1, 2, and 4 between the spectral line frequencies. From this, he concluded that there was a regular ratio in the size dimension of the atoms of various elements. This allowed him to develop a classification scheme where the difference of the spectral line frequencies was inversely proportional to the atomic weight. On the surface, such an approach would probably, at least to a chemist, seem at least odd, if not absolutely absurd. But it turns out that it was very successful in determining which elements could be grouped together or should be grouped together in a periodic system. From this, Heinrichs created a spoked periodic system with all of the groups of elements radiating away from the hub of a wheel, with the lighter elements sort of closer into the hub and the heavier ones farther out. Elements in the same period are placed in the same distance from the hub, creating an easy to recognize system. Additionally, Heinrichs' focus on spectra would anticipate the work of Bohr some 50 years later, when the Danish physicist was developing the first quantum mechanical model of the atom. All of this brings us finally to the two men most universally recognized as developers of the periodic system. The first, Lothar Meyer, was initially spurred to work by Cannizzaro's paper at the Karlsruhe Conference. He described the experience of reading the paper in biblical terms, saying famously, quote, "The scales fell from my eyes, and my doubts disappeared, and were replaced by a feeling of quiet certainty." Unquote. By 1864, he had published a textbook that was deeply influenced by Cannizzaro's work, which relied on a table of elemental organization characterized by increasing atomic weights and the groupings based on chemical properties. Additionally, he incorporated the separating of certain metals into transition groups as championed by Oddling. Finally, he left spaces in his table for undiscovered elements, as was warranted by the data. Meyer's table was characterized by an additional reliance on the periodicity of physical properties of elements, including atomic volumes, densities, and fusibilities. It is clear from his paper published in 1870 that he had fully thought out the table, and it contained more than 50 elements. It was really quite an accomplishment. The final figure in our story is the one person who is most commonly identified with the modern periodic table. Dmitri Mendeleev was born in 1834 in the Siberian city of Tobolsk, and was, by some accounts, his mother's darling among 14 children. Recognizing her son's obvious intellectual gifts, Mendeleev's mother worked tirelessly to get her son enrolled in the St. Petersburg Pedagogical Institute, a school for the training and education of teachers. This fact is profoundly important to the story. As we have seen, a number of the attempts to develop a periodic system arose out of a need to create an organizational schema for writing textbooks. By the 1860s, there was an enormous amount of chemical information, and a teacher had to have some way of organizing it all so that his or her students could both remember and relate to the information. As we all know, information without context is useless, and so there was a need to create a framework within which to place all of the data about the various elements and compounds. It was in just such an attempt to create this framework that Mendeleev developed the periodic table he became famous for. There are a number of differing accounts as to how he arrived at the system, but the most common element to these stories is that he was working with cards with much of the physical and chemical information of each element written onto them. While this story evokes images of a man sitting up late into the evening trying to organize or reorganize the cards in some way, the more accurate picture would be that they represented a decade or more of careful thinking and consideration. While colleagues of Mendeleev reported seeing the cards tacked up on a wall in some sort of table, that was just the end result of acquiring and sifting through a mountain of data to determine what was and wasn't important. One of the things that's really amazing about Mendeleev is the quantity of chemical and physical data about each of the elements he just possessed. It was enormous to understand that he knew what kind of salts every single element might form, what that salt might precipitate when it was dissolved in a solution and then reacted with another substance. Just anything that you can imagine, Mendeleev sort of knew and understood deep, deep, deep down in his bones. It was one of those things that allowed him to see the totality of all chemical information, not just the individual cards. An example some of my older listeners might relate to is how we used to have to write research papers before the development of modern documentation software. What you did is you took notes from your sources on index cards. Often you included quotes or things that you wanted to paraphrase, and that formed a permanent record of what you had read. When the time came to write your paper, you would start by organizing the cards in the order you intended to reference them in the paper. This formed a very rough rudiment of an outline that you then developed more formally. What the cards, of course, didn't record is all the other things you'd absorbed during your reading and research. They didn't document the sort of the paradigm that you had formed, the broad understanding you had developed during your research and that you were working with in thinking about the structure of your paper. Nor did they explicitly show that their organization was actually an artifact of those beliefs about the ideas you had related to the subject. In fact, they only sort of did that indirectly. I think the same is true in Mendeleev's case. His card version of the table was the final product of many years of thinking and sorting data. It held within it the work of others before him, while also reflecting the conclusions he had reached through much thought and contemplation. While he may have finally put it all together on a single day, as the story goes, I'll bet he was pretty far along that road when he decided to blow off the inspection of a nearby cheese factory in an inspired frenzy of intense work to complete the table. Now, interestingly, Mendeleev was neither a fan of Prout's primary substance as protyle, nor was he a fan of the Triads of various chemists. Instead, he focused on the atomic weight as the fundamental property of each atom that remained unchanged. This focus on the foundational physical properties of an element, rather than on the chemical properties, served him in good stead when attempting to understand the periodic nature of the organization of the elements. While ideas such as valency were important, especially when organizing some of these things, Mendeleev understood that things like that, things like these chemical properties, could change in certain cases when atoms of an element combined with atoms of other elements. What didn't change was the atomic weight of the atom, regardless of whether it was found in a simple element or a compound material. A sodium atom had the same atomic weight, regardless of whether that atom was in its metallic elemental form or in combination with chlorine as part of table salt. It was this focus on the physical properties that enabled Mendeleev to leave spaces in his table for missing elements and to predict the properties of those elements. The success of these predictions, as the new elements were discovered over the next few years, was strong evidence for Mendeleev's scheme. While Mendeleev did make a few incorrect predictions in terms of the properties of some of the already known elements, these errors were not seen as being invalidating of the underlying principles incorporated within the organizational structure. As such, the table of Mendeleev was adopted fairly quickly within the chemical world. Just as importantly, the periodic system demonstrated that there was some sort of definitive underlying structure that gave rise to the repeating nature of the properties of the elements. This structure would serve two purposes. First, it would guide researchers in discovering additional elements. Second, it would, in time, provide a way for those who thought to explain the electronic structure of the atom, once the electron had been discovered, to test their claims. However, that portion of the story lies ahead of us, and we'll get there when we get there. To close this story, let me first acknowledge my primary source of material. Eric Scerri's, and I hope I'm saying that name right, but Eric Scerri's The Periodic Table, its story and significance, has been absolutely essential in developing this podcast. I've worked primarily from chapters 2 through 4 of the book. Those interested in fuller descriptions of the ideas of the 6 developers of the periodic system will do well to read Scerri's book, especially in reference to Heinrichs' ideas, which I've only touched on here. Scerri does an excellent job of discussing both the historical and chemical sides of the topic, while also considering the not easy to untangle philosophical perspectives. I would specifically recommend his book, to those studying chemistry as a career, as he thoroughly discusses the development of the ideas that went into the periodic table from a chemical perspective. The second thing I'd like to mention is, as I said in the opening series of podcasts on scientific inquiry, the periodic table is an excellent example of an organizing principle in science. While none of its discoverers understood what the physical laws were that led to its structure, it became a powerful guiding force in directing research to uncover those laws. Produced from an almost entirely chemical perspective with data arrived at chemically, it provides a framework in which to interpret additional results from the investigations in physics that were occurring concurrently and shortly thereafter. Now, it's these investigations we're going to examine in the next 2 podcasts. And I plan to begin with the idea that had a long history of its own that we'll just briefly touch on, and that is electricity. So, next week, we'll take a look at the electrical atom. Until then, full sails on your journey.